You're welcome once again. Let me share the slide. We discussed, we started with risk, because I know that was the last thing we discussed yesterday. We still let's just quickly brush it again. So what I started yesterday, I said that when we finish with the chi-square, I said that when you do all your cross tabulation, trying to look at association text, association between variables, you come with a chi-square p-value, you make your judgment that it's statistically significant or not. We'll see that does not quantify anything. It doesn't quantify how big is the association. The mistake people make is the value of the statistic and the value of the p-value also does not actually quantify it very well. Even though there is a level, at least before you can say something statistically significant, because of the value of the p-value. But there are a lot of things hidden under. Something can be very statistically significant based on the p-value. The p-value is extremely small. But in actual sense, the quantification may not be as much as another one, that even the p-value may be higher. So in that case, the p-value just tell you if it's significant. It's a probability. So that, oh, the probability that this is due to shine is very low, extremely low. That's it. It doesn't quantify the association. So that is why the measure of association now try to quantify it. The measure of association like relative risk and odds ratio. There's another one that is not relevant here unless we talk about survival analysis. That is hazard ratio. So those are the three measures of association. But the hazard ratio is reserved for discussion on survival analysis. But here now we talk about odds ratio and relative risk. So you get to know that relative risk is comparing two risks. Risk amount in a group divided by another risk in another group. Odds ratio is comparing odds in a group compared with odds in another group. And that was why we started with the concept of risk and odds. So what does that risk mean and odds? Risk is actually probability. And odds is risk over 1 minus 3. We discussed that yesterday. That should have for each probability, which is risk, you can calculate corresponding odds. And we all know that the probability is between 0, value of probability, possible value between 0 and 1. Cannot be less than 0, cannot be more than 1. So that should have probability cannot have negative value. And it cannot go beyond 1, it cannot have 1 point something. So ranges between 0 and 1. Odds, the other way, also somebody start from 0 also and end at infinity. And we say relationship between odds and risk. Odds is risk over 1 minus risk. Risk is 1 odds over 1 plus odds. Now, from the table, look at this table on the right side. I was explaining yesterday. If the probability of something, if the probability that it rains today is 0, what is the odds? Please, I want it to be interactive. I want people to, because this is logical reasoning, I want us to reason together. If the probability that it rained today, it rained yesterday, or it will rain today is 0, what is the odds that it will rain? If probability, if the risk is 0, what is the odds? You know it's going to be 0 over 1 minus 0 minus 0. What do you say?
It is 0.
It's 0 because it's 0. Anything you put 0 on anything is 0. Yeah, it's going to be 0 over 1 minus 0. 0 over 1 is 0. And we also know that when the risk is 0.5, that is probably 0.5, the odd is 1. Because if you probably the range is 0.5, so the odd will be 0.5 all over 1 minus 0.5. That is, it will be 0.5 over 0.5, which is 1. We also know that if the probability that it will rain, if it is 1, what is the odds? So who can tell me that? What is the odd? If the probability that it will rain is 1, what is the odd?
1 over 0. That's infinity.
That is what?
1 over 0. But it will be 1 over 1 minus 1. 1 over 1 minus 1. That will be 1 over 0, which is
1.
like point, which is like point something.
No.
It's 1.
It's good. It's good. The discussion is very good. Go on discuss.
It's 1 now.
It's 1 over 0, is it not?
1 minus 1. 1 over 0. This is 1. 1. What over 1 minus 1 is 1 minus 0. Answer is 1.
The answer is 1. Is that the consensus?
It's 1.
Is that the consensus?
Yes.
The answer is 1. The answer is 1.
Who differ? Who differ?
It's infinite.
Eh?
Infinity.
Infinity, yes. How can it be 1? When the other one.
Hello, sir. I went off. I didn't follow the reason. That's what the answer was.
I want you to be interactive. Even though it's not a physics, it's a visual class. So please, the person that says infinity, explain to everybody, please.
Because I said 1 over 0, which is 0 point something. Okay. Yeah, that's
Have you got it now?
Yes, sir.
Yes. The 1 over is 0 is infinity. So that is why when the probability is 1, all corresponding odd is infinity. So look at the table now, you see something like 8 lie down like that. That is the sign of infinity. So odd ranges from 0 to infinity. Probability ranges from 0 to 1. Can you see? Something, and that was why I showed you a graph yesterday, which I will repeat because I want it to stick. So look at this down, it says odd probability of event over 1 minus probability of event. I also use as a picture here, histogram here. Odds, probability is this red area. So probability will be this, if the event happen is the red area. This is a circle now. The other area that is not painted is that the event did not happen. The probability is, the example is that the number favorable to the event happening and the total over total. That's how we calculate probability. Why the odd is, it happened all over, it did not happen. Can you see? And you see later, when the odd, even now you see, when the odd is close to, is very small, and when the probability, the risk is very small, the odd, the value of the odd is close to the probability. If you can see on the table, when it's 0, both of them are 0. When the risk is increased more, the odd also will increase more, but the odd will be more than the risk, but it's close to it. But as you are increasing the probability, the difference between the odd and the probability increases. To the extent, look at what happened now. It's like the odd is moving at a faster rate than increases at faster rate than the probability itself, the risk. When the odd is halfway, because the risk is halfway, because the possible value is from 0 to 1. 0.5 is the halfway. The odd has reached 1 from 0. Can you see? When probability is 0.5, the odd is 1. So that is the odd has traveled double distance when this one has moved halfway. So the remaining halfway for the risk from 0 to 1, the odd moves to infinity. That is the logic. And if you look at the graph, if you plot odd against probability, you will see flattening. That is, when probability is 0, the odd is 0 also. When probability increases, the odd is decreasing small. Can you see it's lifting up small? When it is now the odd, the probability is 1, is close to 1. Can you see the odd is going to infinity? That's why it will never touch, that graph will never touch that 1. Because when odd, the risk is 1, the probability, the odd is infinity. And the intelligent people say, how do we say? So it shows that the graph is skewed. So we have a better graph. So and I showed you yesterday the logarithmic scale. Logarithm, the way logarithm of 1 is 0. So if you look at this scale now, you see that they change the odd to log odd, calculate the logarithm of odd. So if you now plot probability itself, it's not log probability, log the probability itself against log odd. So they now make the graph to be symmetrical. And you see, look at Ogive graph. This is a cumulative frequency curve now. Can you see? So to make it, if they decide to plot it as a frequency polygon, it will follow normal distribution like that. That is why when something does not follow normal distribution, if it's skewed, you can do log transformation. We did that for the training we did on SPSS, how to use SPSS, to do some summarization, descriptive statistics. We use it in the training. Some of us were there. They are present there. They were present, so they will appreciate it better. So that's why we use logarithm, natural logarithm, to know when something is positively skewed. You use to correct it, because what logarithm does is to bring extreme value and bring it down. The small value, stretch it out, so make it symmetrical. Look at it now. At 0.5 probability, the corresponding odd is 1, and logarithm of 1 is 0. Can you see that? That's why log odd is 0 here. So that's just, and by the time we get to, anytime we have training on logistic regression, that is the basis of the logistic regression. Now, let's now talk about risk ratio, relative risk, and odd ratio. Relative risk is also known as risk ratio. What it does is to compare two risks. That is, you calculate two risks, you compare them, which one is higher. And the way to compare them here, they use, instead of using subtraction, you divide. Know there are two ways to compare two things. If you want to, you can remove, if you remove one from the other, the smaller one from the bigger one, whatever remains, oh, that is how, what this one is more than the other one with. If it is bigger one, you remove from the small one, you give a negative value. But another way of comparing is to divide. If you divide, put something that is higher and put something that is lower in numerator, denominator, you will get a value greater than 1 because the numerator is higher. But if you put the smaller one as numerator and the bigger one as denominator, you get 0 point something because you put the smaller one as denominator. So what's the odd ratio or relative rate, or what you do in relative rate, is to calculate if you feel that some people are exposed to a particular factor that will cause an event, and some people are not exposed to that factor. You calculate the risk of the event in both, and now put the one you feel should be higher. You feel it may not necessarily be higher. The one you feel should be higher, and put it as the numerator, and put the one you see should be lower as denominator. You compare them. If you get 1, you divide two things of the same value, you give you 1. That shows that the risk is the same on both sides. But if it's greater than 1, it means that it's higher for the numerator. You still get to know it. So odd ratio is the same. So both of them are measure of risk. We're going to explain the difference between them. So relative risk, also risk ratio. Because ratio, we say ratio is dividing two things of the same unit. So if you calculate really a risk and calculate another risk, divide by risk, that is ratio. That's why you can call it risk ratio also. So relative risk relative to the other, comparing the two. So both names are correct. The same thing, the odds ratio is also relative odds. It's only the relative risk stick to comparing risk, and odds ratio stick to comparing odds. So both of them, they are relative and they are ratio. Relative risk, relative odd ratio, risk ratio also. You can use the name for both of them. So odd ratio is used when occurrence of an event instead of a disease cannot be calculated because the event has occurred in the past. So we talk about risk. Risk probability is about the future. If something has happened, you cannot calculate the probability. What are you calculating probability for? It has happened, right? So it has rained. That's what is the probability that it will rain today? It has rained. But for the odds, you can calculate if it has not happened. After you calculate the risk, you can calculate the odds. If it has happened, of course, you know the risk. You can calculate the odds. So odds can be calculated whether the event has happened or not. The risk can only be calculated when the event has not happened. So that is why comparing risk in between two group of people, or yes, group of people, is only meaningful when the thing has not happened. So in a study where you look forward, that's where you can compare risk. What they call prospective, like cohort study, like experimental study. Because in experimental study, you do something to people you are looking for to capture, even though initially you see you have taken some measurement from them. But you do something, you now take measurement again. So in between the start of your work and when you take measurement, you are looking forward. So you can calculate risk with experimental study. Cohort study is the same. Cohort study where you select people you look at are exposed to a particular factor. You also select people that are not exposed to the factor. You look forward to know in future how many of them will have the event. So can you see? So the risk, relative risk, is now used. That is, comparing risk is useful, only useful when we are dealing with a cohort study or experimental study. Why odds ratio is used for any of them, any study. So odds ratio is more universal. But the issue you're going to get to know that odds ratio is a proxy, because odds, calculating odds, is a proxy to risk. So it's better, as you can see, the risk is the real thing. But you know that when you calculate the odds, the value of the odds is not the same thing as the risk. But if the attribute is low, like if the disease is rare, the value of the odds is close to that of the risk. When the disease is common, the event is common, if you calculate odds, it will be far away. Just like you see now, when the risk is 0.5, 50%, the odds is 1. When the risk is 0, the odds is 0. When the risk is 0.1, the odds also will be higher, but it will still be close to the risk. But as the risk is going higher, the odds is higher and it's far. The value is far. You guys will talk much about that later also. So what I've explained now, for odds ratio, comparing odds is more useful with case control study, with cross-sectional study. But even experimental study and the other study, cohort study, you can compare odds. But why should you? Because the odds, the value will be different from the risk. If you can calculate the risk, because the risk can only be calculated in those type of study. If you can calculate somebody is disturbing, If you can calculate the risk, why are you calculating the odd? So if you can calculate the risk, there's no point of calculating the odd. You get the risk. So if in a situation, it's only in a situation you cannot calculate the risk, like in case control, in case control and cross-sectional analytical study, you cannot calculate the cross-sectional study, you cannot calculate the risk because the thing has already happened. Both case control and cross-sectional, it has already, the event has happened. In that case, you calculate the odd. You use the odd instead of the risk. So you now calculate the odd ratio instead of relative risk. This is what I just explained now. Risk can be calculated only from the data captured when the event has not occurred. Like for example now, look at this situation, prospective cohort, risk factor, clinical trial. So it's talking of cohort study and experimental study. When you see CRA, it's experimental design. But if you look at it, say prospective cohort, even here, even the retrospective cohort also, you can still calculate because that risk factor also, it has been captured is in the, if you are doing retrospective cohort. What has happened is that in the past, they have recorded the risk. In the past also, the event had happened. The record is there. So you can still use it to calculate the risk because you have record when the event has not happened, the record of the risk. And when the event happened, the record of the event has been there also. So you can still calculate the risk also based on the record you have. But that's why it's retrospect, you are looking backward. But for the case control and cross-sectional study, the event has happened, you can only calculate the odds and calculate the odd ratio. So you cannot see now the situation where we can use relative risk. Relative risk is core study, experimental study. While odd ratio is, when you cannot calculate risk now. You cannot calculate relative risk, like in case control study and cross-sectional study, you calculate odd ratio. You can also calculate odd ratio also even in the other study. You can also calculate odd ratio because it is easier. You see, most of like for logistic regression now, either you are using it to run experimental design or cohort study or case control cross-sectional study, the statistic is odd ratio or logistic regression. So even if it is experimental design, it's odd ratio. But of course, you know that the value of the odd is quite different small from that of the risk, depending on the variation in the value depends on the how common the disease is. If the disease is rare, there's no much difference. But when the disease is common, the probability is high, the difference is much. So occurrence of event are as a result of exposure to certain factors. Of course, we have said that the relationship between exposure to a factor and occurrence of an event can be depicted in 2x2 contingency table. You know, the factors expose, not expose. That is for the factor. Disease, occurrence of the disease, not disease. Event may not be the disease anyway. Event happen, it didn't happen. Married, not married. Sack, not sack. Graduated, not graduated. So any event can be pass or fail. So the event, you make it two. Like even if what we underlying variable is a continuous variable, clinician knows how to do it. Like diabetic now. What is the underlying factor? It's the blood sugar. Blood sugar itself is continuous variable that infinite possible number of blood sugar you can have. But they just they do their study from their clinical agreement and many things. That's 126. So once the blood sugar is above or equal to 126, is diabetic. The rest not diabetic. So that is the event. That somebody is diabetic is event. When we discuss probability, even though in fact I shared this slide with you because when Dr. Olagboye is always on the move. He has quickly gone through what we have done. Say, can you send the slide for the so that's why I forwarded the slide to everybody. Because if you look at it, it's only one slide for the one that I say is actually only one slide for this training. 2 slides, this one and that one. Only one slide then. Then, because I explained something from probability and normal distribution, that is one of the one I gave during Tuesday and Thursday. So, and now send that one also. In that slide on probability and normal distribution, I've explained all these things, talking about the cutoff point, the probability distribution. A lot of things I explained there. Because the diabetic, non-diabetic, the continuous, diabetic, the blood sugar is a continuous variable. But once you cut it off, you say diabetic, non-diabetic, you have dichotomized continuous variable that become categorical, binomial. So in looking at the relationship between factor and exposure, a factor which is exposure and outcome, the event, you look at 2x2 table. You try to dichotomize event occur, didn't occur. And there I talk about in the probability, if you read it very well, the languages used in probability, results, outcome, and there's a difference between outcome and event. Outcome, like the blood sugar now, the outcome of blood sugar is going to do blood sugar is 130 milligram per day, 90 milligram per day. That's the outcome. That's the result, outcome. But that somebody is diabetic, it's an event. Somebody is not diabetic, it's an event. So we won't be talking about that now because that one is subject for that. So now, the row represent exposure. We have said that one yesterday. And then before you say that, when you are having your contingency table, make the row the exposure, the column your outcome, which is the event. So by notation, A, B, C, D, put on the cell like that. So the total, we use the total, but when you are talking of 2x2 table, you have 4 cells. Any other thing, like this one, this table now is not showing the total, but the system may be there, but what you are interested in is the A, B, C, D. Now, if you look at it, okay, me, I like real life something rather than, because I want you to look at the formula, we'll come back to their formula. I want you to look at the real life data, the example, look at it. Look at this example now. A is 25, B is 475, C is 5, D is 995. So what this one is, smoking is the exposure here. Lung cancer is the event, the outcome. So this A, it means the people that smoke, yes. And lung cancer, yes. They smoke, got lung cancer. This B, 475, is people that smoke, they didn't get lung cancer. And this 500 is the addition of the two. So this 500 is people that smoke, out of which 25 got lung cancer, 475 did not get lung cancer. Look at the no here. This say C, no smoking, but lung cancer. This D, 995, no smoking, no lung cancer. And the total that this smoke is 1,000. So out of 1,000 that this smoke, 5 lung got lung cancer, 995 did not get lung cancer. So you can see the total that got lung cancer, 30, 25 plus 5. The total that didn't get lung cancer, 1,470, 470. And the total you are dealing with is 1,500. Now, what is the risk? If you want to calculate relative risk mean, your relative risk just mean, okay, we are trying to see does smoking cause lung cancer. So you calculate risk among those who smoke that they are exposed. And now divide it because that's what you expect. You want to see that smoking cause lung cancer. You now use the risk among the exposed as the numerator. The risk, you calculate risk for the people that were not exposed, you use as denominator. You want to see if actually smoking causes lung cancer, the risk should be higher among the people that are exposed. To be higher, said the way that when you divide, it should be greater than 1 because the numerator. If it's higher than the denominator, it should be greater than 1. But if it's the same, when you divide, it will be 1. It shows that the risk is the same for both of them. But if it's greater among the people that smoke, it will be greater than 1 because the numerator will be greater than the denominator. But even if the risk is even less among the people that smoke, what will happen is that the numerator will be smaller than the denominator. When you do it, it will be less than 1, it will be 0 point something. That's the logic. So let's look, how do you calculate the risk among the exposed? It's very simple. Look at the total here, 500 at the exposed. The risk is 25 over 500. That's the probability that the person that smoked have lung cancer, 25 over 500. The probability that he didn't have lung cancer is 475 over 500. But if you look at it now, it's logical. The probability, you can also get this probability for this one by removing the probability that there's one from this one. Remove 25 from 500, it gives you 475. So the probability that the person have lung cancer and the probability that the person does not have lung cancer, when you add it together, it gives you 100%. So the risk now, that's why you see, the total here, the 500 is represented by A plus B because this is A, 5 is A, 25 is A, 475 is B, A plus B is the 500. The same thing here, this is C, 5 is C, 995 is D. The total for those that are not exposed is A, C plus D, 1000. So the risk among the exposed is A over A plus B, that is 25 over 500. Can you see? And the risk among the non-exposed is 5 over 1000, which is C all over C plus D. Look at it. That is the formula for relative risk. If you calculate it now, you do it, you know, the way you change subject of formula, 25 over 500, everything over 5 over 1500. So when you want to change the division to times, you swap the numerator and denominator. It becomes 25 over 500 times, instead of saying 5 over 1000, 1000 over 5. If you do it, it gives you 10. We have already solved our example. And what I just want to see is this formula. I see relative risk is A over A plus B, everything over C plus D. That's just it. It's very simple. So me, I like explaining, not just from formula did not come first. Actually, the written concept we just represented by formula. So that is for relative risk. So if somebody want to ask question, so let me pause. Ask your question before we proceed. Somebody want to talk.
Clear. It's clear. No problem. Very clear.
To everybody.
At least
if you have question, please don't hesitate. Or maybe let me check if somebody send chat, because some people may not want to ask. I saw two chat. You may not want to ask like that. Okay, somebody saying it's on duty. Has he joined? Okay, yeah, you have joined. Okay, you're welcome. Then, okay, the same. Intermittently, okay, no problem. But you have question? Do you have question? Please, if you have. Dr. Afefi, do you have question? Okay. If you don't unmute yourself, I will not hear you. Okay.
No question, sir.
Okay, that's
no
great.
No question, sir.
Okay, that's great. Let's continue.
Okay.
Yes. So we have looked at the way you get the relative risk now. Let's look at the odds ratio. Look at it. I would prefer also, first of all, go and check example before I come back to the formula, so that it won't look like a something that somebody just control. Look at it. Look at this. A, B, C, D. Also, the A here is 45. This B is 60. C is 5. Then D is 90. And it's about smoking and lung cancer also. But it's different from the other one. The example I'm using here, but it's the same. So if you look at it, Odd. What did you say odd is? Odd is probability over 1 minus probability. If you whichever way you solve it, you know, we said the probability, if you remember, if you want to calculate risk for this expose now, it will be 45 over 105. That's probably 1 minus probability will be 60 over 105. Or if you say 1 minus 45 over 105, it's the same thing as 60 over 105. So if you now put 45 over 105 divided by 60 over 105, you see that 105, 105. By the time you change of it, you cancel, it will become 45 over 60. Can you see now? That is the odd here. And there are this odd, there are two approaches. All the approaches, they end up in the same way. So if you look at 45, if you follow what I first said before, just say, okay, 45 over 105 divided by 60 over 105. Or you say 45 over 105 divided by 1 minus 45 over 105, because that is the probability of not the event has not happened. 1 minus p. Whichever way, it will give you 45 over 60. You do the same thing this for these people that are exposed. For the people that are not exposed, it's the same. But there's another way also. You can say the risk is this, you can say this over this divided by, okay, the ratio. Okay, just leave that one. So if you, let's say you calculate the odd for this and odd for the other, you divide it. It gives you, can you see? It end up giving you AD. Can you see the multiplication now? It will be cross, that's why they call it cross product. 49 times 45 times 19, A times D divided by 60 times 5, B times C. Can you see? So that's why I say AD all over BC. So for odd ratio, AD divided by BC. But for the relative risk is A all over A plus B, everything over C all over C plus D. That's relative risk. Odd ratio AD all over BC. Because A all over B divided by C over D. Does it make sense? Now, if you look at it, I was saying there are two approaches to it. You can say, okay, if you are, but it's the same thing, end up with the same thing. If you say, okay, odd ratio for case control study, just say A all over C. If you even say, because the reason you can use the two approaches that the one I just explained is this one, odd ratio for cohort study, A all over B, everything C all over D. But in the case control where the risk has already happened, you can just say, okay, A all over C, that is, among the event that have the event, what is the odds that the event has happened? A all over C divided by among the people that didn't have the event, B all over C. If you look at it from there, it will still give you AD all over BC. Can you see? Both of them lead to the same thing. And that is why they call, as a place that they say, odd ratio is a cross product. Can you see? A times D, just say A times D divided by B times C, cross product. That's it. So that is how they got to know that it's a cross product. But you know many people, what is all the AD all over BC? The cramming is good. But it's good to know the logic. Now, after calculating the odd ratio, well, I just put this one here for academic confidence for you to calculate 95% confidence about standard error. I will not be explaining standard error here because in under hypothesis testing assumption, I talk about standard error. Under inferential statistics, I talk about standard error. You know, there are some assumptions in the particular, like when you are in somebody is in SS3. It's not everything what you're supposed to know in GSS3. If you start explaining it also, you spend all the time explaining down without moving forward. But just know the computer will give it to you through all this one. Now, let's just quickly look at example and how you run it. Just know that relative risk is you calculate risk. So this is how you use the hand to calculate it. We just demonstrated now for the two of them, how you use the hand to calculate it. This over this, and you calculate it. But of course, calculating with calculating the confidence interval is a lot of there's a natural logarithm involved. There's no need burden yourself, but how to interpret it, I will explain, because the computer will give it to you, the confidence interval, and how to explain it, explain the result. Before we go on to run it, does anybody have question? The one we just discussed. Does anybody have question? No question. So it's so clear. There is no question. If you are talking, you didn't unmute yourself, I will not hear you. So if you want to talk, unmute yourself. Okay, let's continue. So does any, I want to, okay.
Okay, so it's still back to the odds ratio, because I know there was something you were explaining when you showed that box. You were saying that if, for example, in the box that said, like this one now, that said, yeah, that has the yes, no to lung cancer, then smoking, that if you say 25 over the total divided by, for example, 475 over 500,
yes,
then divide, so like,
it still
if
come back
the
to the
way you
same
get
thing.
that value,
Okay,
then
don't worry.
divide it.
I know what to do. Don't worry. Just wait. Just wait to explain that to you. I know what to do. Don't worry. Because those are mathematical. Yes, we have a body. So what I'm saying is that you know you have this.
Yes.
This is A. This is B, right?
Yes.
This is C. This is D. And this is
yes.
A plus B, which is the 500 you're talking of. The total here. This is A plus B. This is C plus D. The total that are not exposed.
Yes.
This is total exposed and not exposed.
Yes.
So that's 500. This is 25. What I was saying is that if you say 25 divided by 500,
yes,
which is the something, and I say everything 9, is it 9 or 5? 5. The other one is 5 divided by
and
9.
This 5
is,
okay.
9,
No,
9,
continue, sir.
Yes. What is it?
No.
What is it?
No, you said so. I was trying to look at it. What I was trying to look at
it. Sorry. This one. Sorry. This one is 20 making 475 rather. 475, right? Abi?
Yes, over 500.
Yes, thank you. Don't worry. I've gotten you. I just over 500. In mathematics,
yes,
25 over 500. So you know, this one is not like writing with your distance. Just
I know.
Times instead of division, and they say times. You know, this 500, the denominator will become numerator.
The numerator,
yes. 500
divided by
45, 475. So 500 cancel 500. It becomes 25 over 7. So that is right. Can you see now? So you still come back to 25 over A over B. I don't know if you understand now. It will still come back to A over B. Because they are having the same denominator. And the other, the down division, mathematically will come, it will cancel these two. It's the same thing. You get it now? It's the same thing for this one also. Does it make sense now?
Yes, sir.
Because I know when we were talking, I know that was what, you know, sometimes in the advanced something, you know, if you can't remember your elementary something, it's good to break it down like that. You know, sometimes people just assume that the space, you have gotten it, you just move on. So that's just the logic behind it. And the same thing for this other one. So by the time, that is, this one is the risk among the exposed. If you do the same thing, C over D will be the risk. C all over D will be the risk among the non-exposed. You get it now? So at the end of the day,
yeah.
Okay, I think we
Thank you, sir.
Welcome. Any other question? Any other question? No question.
Okay, we are home and dry.
Home and dry. Okay. Okay, let's do this example. The first one, in a study, 500 smokers and 1,000 non-smokers were followed up for 10 years to see how many will develop lung cancer. This was very clear that it's a core study, it's a longitudinal study, it's a prospective study. They follow them up. If 25 of the smokers and 5 of the non-smokers develop lung cancer, respectively, what is the relative risk of developing lung cancer following smoking? I also calculate the odds ratio. So if you look at the calculation now, this is what I explained before. And you see what we just did now, Dr. Ugo. Dr. Ugo.
Yes, sir. Yes,
what
sir.
we just did now, this is what we just did now. 25 over 500 divided by this over this. And as we finish, everything is 10. The risk among the exposed and the risk among not exposed, everything is 10. Then you calculate the odd ratio for it. It gives you 10.4947. You can see that the odd ratio is slightly higher than the risk now. Can you see?
Yes.
That's what you expect. But we're going to know more about it later. Because we know that the odd ratio is from 0 to infinity, while the risk is from, even the risk, sorry, that one is odd and risk. Even, I'm going to explain something also later. Sorry, I'm jumping this up. You know, the relationship between risk and odd is what I explained. Risk is between 0 and 1, or is between 0 to infinity. Even you're going to see that relative risk also, you're going to see later that the range of value is limited, but the odd ratio also range from 0 to infinity also. Odd ratio itself. The risk is not like that. The relative risk is not like that. So without much ado, who downloaded what we have done? So the person will share, because I've done the talking, you should do the analysis. Who downloaded? I share data for today. Sorry, I forgot to share. I will have shared together with the others, so that I forgot. I now remember I didn't share those measure of association data. Who downloaded? Dr. Ugo, are you using your computer today? Dr. Ugo.
I downloaded it. Sir, I downloaded it, but I'm not using my computer for Zoom.
Why? You started again. I will not answer your question again because you asked questions.
You don't want to participate. Okay, sir, you know what, sir, maybe is it possible for you to send that invite to my mail? Because I've been trying to send it from my WhatsApp to my mail. So let me see if I can try and open Zoom like on this my laptop.
Don't worry, that one is, you cannot be doing that one. Don't worry, leave that one because the time is gone. Dr. Anulika, Dr. Wobi.
Hello, sir.
Yes, sir.
Are we talking of the SPSS or which other one?
It's not SPSS. This one is the data file for today. I send it today. I send the data of 2 lung cancer smoke, smoking lung cancer and lung cancer smoke.
Yes, I saw it.
But you don't have SPSS installed now. You cannot do anything for us. What of Odirichi? Boju, you want to share with us?
My laptop.
Doctor, okay. Doctor, okay. Nwobi want to talk. Dr. Nwobi.
Yes, the one you sent to me, I couldn't even open it. I couldn't do much with it. Even other files you sent, I discovered that I could not just open them.
It's your computer then, because other people open it. You know what I sent? I didn't send to individuals separately. I put all the mail there, then send in box. So if some people receive it, some people cannot open it. There must be problem. Because if it's the problem is from me, everybody will have the same problem. They will not be able to open it or download it. So what of
actually came like a forwarded message text to.
Okay, listen. I know the problem you have. I know the problem you have. That was the problem your friend Odirichi has also when I was in it. So when I forward a mail, listen to me. When you forward a mail, if you receive a trail of mail that has been forwarded before, for you to know get the attachment, you have to click on the one they sent to the first person. That's where the attachment is. You get it now. If the mail was forwarded to you, the attachment is not where your name is. Under your own name, the one sent to you will not see the attachment there. Now go and click on the first row. All the people that send the mail, you see their own name, their own mail. You click on the first one. That is where the attachment is. That's how to manage mail. You get it now? Because if I have attached the mail I sent to some people, there's no point wasting my time attaching the same something all the time. I want to send some to somebody. I will just forward that one, unless if I want to attach new thing. So I think it's the way to manage mail now. Dr. Emeshebe, did you download it? If you don't unmute yourself, I will not hear you. Some people they just left their distance. Dr. Enshaw, are you okay? Okay. It's the same set of people that is okay. Dr. Emeshebe. You want to share with us? Do you want to share it with us? You are not answering. Okay, he's not answering. Dr. Olagunjoye, maybe we share your own. It's lung cancer smoke. Yeah. Smoking lung cancer. That's the first one. Smoking. No, there are two. Smoking lung cancer. That's what we want to do now.
So can I share if nobody's ready?
Okay, you can share if you have it. You can share. Smoking lung cancer. Thank you, sir.
Okay.
That's great. Thank you, sir. So,
yes, sir.
Yeah, thank you, sir. You see, we have the variable after the serial number: smoking, then lung cancer. We have 1 is yes and 2 is no. If you click on the view, sir, view, you see the labeling. View on the left after edit. View up.
Is it this one?
No, left upper corner. View. Click. No. Go back to data view. View left upper corner after file and edit. It's after file and edit. View. Yes, thank you.
Okay.
And then click on. Okay. You already done label, value label. Yes, that's what I want them to see. Value label. Can you see? So it's label. You may remove it if you want to remove it. But it doesn't. Let's continue.
Okay.
Yeah. So you don't need to go and do it before you run your analysis. I just want people to see that the way it's coded. If you don't want to see the yes, no, the coding, you go back to the view, you remove it. Just like the what you did. Yes, you can actually do it here. Thank you. I even do it up here. Yes. So let's go to analyze. descriptive cluster. You see, because it's about contingency table, it's still cluster. Then we move smoking as the row. Column,
That's the
yes, that's the exposure. The lung cancer is the outcome column. And let's go to statistics. You now click on risk. If you want to do all these chi-square, you can see, you can click on chi-square, but yeah, you can click on it. Let's continue. If you want to click on cell, and put the row, relieve the expected row. Yeah, thank you. Let's continue, sir. So okay. So it's not the chi-square we're after. Those are you can do a lot of things with it because it's independent group also. It will give you share something with us, the view, the result.
Yes, sir.
View.
Did you click on row?
Yes, now. Yeah, that's nothing to do with this result because what you need the risk. Once you calculate the risk, the other one is just paraphernalia. You don't actually need to calculate the risk.
Okay.
Let's scroll down because this initially because we keep. Thank you. The last table is what we actually need here. All these other ones just do the chi-square with your look at it. You show the chi-square. Look at the Pearson chi-square, a yet corrected chi-square, likelihood ratio chi-square. All those things statistically significant. If you are to analyze, it is statistically significant. And that's all it gives you. But let's come to the risk estimate. You can see. Remember, look at for cohort lung cancer is equal to yes. Can you see the relative risk? Relative risk 10. Look at the 95% confidence interval. Then look at the odd ratio we calculated 10.474 and the confidence interval of it. So this is how to run it. So I want us to, because I will come and explain the results. I want us to do the one for the odd ratio also before I come to the theory because the result, the interpretation is the same. The interpretation of odd ratio and relative risk is the same. So we'll come back to the interpretation. You can share, sir. You can stop sharing, sir. So I don't know if there's any question in the process. The way you go about it, very simple. No question. So no other person. The other one.
Yes, sir.
Yes.
I noticed that they used odds ratio, and you kept on saying relative risk. Is it because it's tied to the fact that you mentioned that they can be used? They are equated to each other as the odds ratio and the.
I don't understand what you mean. You say that the first sentence you say you notice that. Repeat the first sentence you said. I can't hear you. Unmute yourself if you want to talk. Ugo. Maybe it's not hearing. Ugo.
I don't think so.
Because I noticed him say relative risk, but what we have in that output table is odds ratio. So that's how I needed that clarification.
Okay. Dr. Prof, please help us go to that. Though I have the output on the slide anyway. Don't worry, let me just show the output on the slide. I have it, the same output on it. Let me just show you. For me. Okay. Okay, look at the output. Can you see it?
Yes, I can.
Yeah.
Yes, sir.
That first one, you see that they put, let me bring my annotation. That first one, you see they put odd ratio. That's the odd ratio. This one,
Yes.
for God, is only the label. You need to understand. You know, the people that did the software, they are not necessarily statistician. They are programmer. Though they have statistician to advise them. Sometimes, so that's why they keep on having version maybe to improve the get. Maybe you as a user now you can tell them, why don't help us label this thing as risk? Eh? If these two,
Okay, I now understand.
so the second one is the relative risk. The third one also is a relative risk. If what you are putting forward, what you want to know, as the first exposure, you know we have the exposed, not exposed. If you want to compare, you want to
Yes.
put people that are not smoking, you want as numerator, and the people that are smoking as denominator. That is the second one. Can you see?
Yes.
It's the second one. So you know, because the risk is lower among the people that are not smoking. If that is the one you put as the numerator, this will be the relative risk. The relative will be less than 1, 0 point something. Can you see now? That will say, all for lung cancer, all for lung cancer, no. Can you see now? All for lung cancer, yes. Then all for lung cancer, no.
Yes.
So if you want to see, maybe you want to see lung cancer, that is, you want to see the smoking, does it cause lung cancer, or the smoking prevent lung cancer? This second one is testing if smoking prevent lung cancer. Can you see?
Oh, yes, yes.
So
I don't understand.
People is putting the odds of the people that are not smoking as numerator.
Okay.
That's just the essay. So that's why they give the 3 results there.
Okay, I don't understand. Okay.
So
Thank you,
now,
sir.
yeah, so that's why you need to understand. That's why understanding the software then with your knowledge, statistics, they go together. You must be sound in your statistics. Once you understand, okay, you now say, okay, this is odd ratio. This is relatively, the first one is odd ratio. Don't worry, I will say something later after let's run the odd ratios home. The other one, the second one. Go to see the similar result also like this. Let's run it before I give some explanation.
Okay.
Okay. You can stop sharing, sir, Prof. So who will share the other one with us? The second smoke, lung cancer smoke. It's a Meshebe. You are just appearing. Did I pin you your video? You are just appearing. Do you want to share it with us, Dr. Meshebe? Because I'm not hearing you talking. Okay.
Maybe she's not with her phone. Maybe she just put it on and stepped out.
Okay, no problem. Let Dr. Olagunjoye share with us there, or Andrew. Share with us lung cancer smoke, the second file.
Okay.
Hello.
Yes.
Hello, sir.
Yes.
I'm actually responding, but it's like my speaker on my laptop. So I'm connecting with my phone now. Sorry about that.
Okay, no problem.
Yeah.
Yes, that's great. That's Dr. Odirichi. Yes. Now,
That's Dr. Mechebe.
no, who is
I'm
sharing now? Who
responding
is
to you.
sharing? Who's sharing? Is a Meshebe that share now? Is Dr.
No, I'm not
Odirichi?
sharing anything yet. I'm just saying I was hearing, but
I know
like
you are the
you
one
weren't
talking,
hearing.
but the Odirichi was sharing. That's what I'm saying. I know that you are the one
Okay,
talking.
okay.
Yeah. Dr. Odirichi sharing. Thank you. Then let's go to analyze straight now. Yes. Let's go to analyze straight. Go to analyze.
You're already there.
It's not there. Okay. Then cross tab. Okay. Move the lung cancer. The smoke is the row, lung cancer column. Okay. Please, okay. You know, mute yourself. Dr. Odirichi is affecting my voice. Mute yourself. As you are doing it, you can mute yourself. Okay, thank you. Now, risk. Just click on risk. Just forget about yes. Continue. Yes. Okay. So share the result with us. New chair. Share the result view with us.
It's not showing. This one is not showing.
It's okay. Show now. It's showing. It was just trying to share. So it's like it's very enlarged. What happened? It's zoom. Okay, thank you. Yeah, that's great. So scroll down for us. Yeah, that's great. It's okay. And you see you will see that look at it the same way, because the computer, somebody is speaker is on. Please, everybody mute yourself. Why did you stop sharing? No problem. Let me share my own because I have the result here. Let me share the results, explaining what I want to explain. So look at the results. Yeah, Dr. Odirichi just brought out. This is the way the result look like. The odd ratio is 13.5 and relative risk is 8.13. You see there's a difference in the value also. Now, I want us to do something. I don't know if there's any question from what, because I want to explain something. Is there any question on what we have done now? Look at the odd ratio we calculated is the same thing. The 30.5 relative is 8.14. The same thing we calculated the hand and the computer brought out. So, Dr. Okay, you can stop sharing, Dr. Andrew. That's great. Now, I want us to do something. Okay, did I say you should stop sharing? Okay, Doctor, who did Prof? Can you share your own, Prof? Prof, Professor Dokidem. Okay, maybe it's not there.
Okay, sir.
Share that one you did the other time. Just share the something so that I want you to go back. I want to run another thing. Share that one.
Okay.
Hope everybody is following.
Yes, sir.
Okay, thank you, sir. Now,
Okay, sir.
I want you to go back, analyze. Go back to that place. That is cross tab. Yes. Okay. You are instead of okay. Put you are sharing. This one is the other one. Okay, no problem. It doesn't matter. Okay, put it there. It's the other something you are sharing. It's not the one you shared before. They put it smoke. Then instead of lung cancer, put that lung cancer logistic. Go to statistic and put the risk and just go. Just forget about all those other things. Risk. Continue. Click. Yes. I don't know if you people see this result. This one that the prof just did now is the same file. Oh, are you listening? Is everybody hearing? Because the network is. If somebody
Yes,
can hear,
I
just
can
talk.
hear you.
Okay, thank you, Dan. Thank you. You see, this is the one Dr. Odirichi just run, and that's what Prof run. But if you look at the odd ratio, is different from this odd ratio and relative risk. There's a swap. Can you see? Before, the odd ratio
Yes,
was
sir. Yes, sir. We can.
13.5, is now 0.074. The relative risk was 8.13. It now became 0.603. The swap, what was here before be turned here? I don't know if you understand what I'm saying. The cohort, the lung cancer logistic. Can you see now? Lung cancer logistic, can you see? So what he's telling you is that this odd ratio is still the same thing, but I just swap it. So I will tell you something. I will go to use this one to explain something. Okay. Prof, or maybe another prof.
Yes, sir.
You know, the one I wanted you to read was the one you did before, the smoking lung cancer. So do that one. Run that one now for us. Don't
Smoking
worry. Yes, the other 5, smoking lung cancer.
Okay, I should run it.
Yeah, run it for us now. Yes. Go to.
Okay, analyze.
Yeah, go to the same thing. Just do the same thing. Then return that lung cancer and put lung cancer logistic. Thank you. And click. No, you say the thing is already there. Don't worry. Just okay. You can check that one. Okay. Just say okay. Share the result. Share the result view.
Okay.
I'm going to explain something.
Is it this one?
Yes. Can you see? Now, if you look at it now, you can see that what happened to the last one you did. Look at this one now. You see, before the odd ratio was 10.474. Now, the odd ratio is 0.095. So what you can do, if you put the reciprocal of this one, if you say 1 over 0.095, it will give you 10 point that thing. So it is just giving you the reciprocal. Look at the odd ratio before was 10 here. It now is 0.955. What was here before was 0.955. It's become 10. Are people following me?
No, sir.
Okay, yeah. So what I wanted to say here, you go to see, okay, Prof, on stop sharing.
Okay.
We'll refer to them later. Let me go on to explain what I want to explain. Yes. Let's look at the interpretation of our result now. All the result we have done. Let's interpret. Now, if look at one here, if the relative risk or odd ratio, it's just the way you calculate it with that differ. Running it with it's just the same. Running it on the computer, it's just the same thing. The interpretation of result is just the same thing. Just the logic behind his calculation that differ. If the relative risk or odd ratio is close to 1, it means that there's no association between exposure and development of disease. A relative risk or odd ratio greater than 1 indicates a positive association between the exposure and the disease. I think I've explained it before. Because if you say, okay, you put the numerator is the exposure, the people that are exposed. The denominator is the people that are non-exposed. The risk among the exposed over the risk of non-exposed. If the risk is higher among the exposed, which is the numerator, it will be greater than 1. When you divide by smaller thing, it will be greater than 1. It shows that that exposure is causing the disease or causing the event. A odd ratio or relative risk that is a relative risk or odd ratio that is less than 1 means the exposure is associated with a less disease and may be protective. That is what I just want to show by asking Prof to rerun that thing. What I just did is to exchange it, putting the people that are not exposed over the people that I don't know if you understand now. So what I did is to now put the numerator, the unexposed as the numerator and exposed as the denominator. It will give you odds ratio that is reciprocal, odds ratio or relativity that is reciprocal of the other one. What is reciprocal? 1 over something. If you divide 1 over 10, what does it give you? I want you to respond because I don't want to quietness.
0.1.
Okay. Okay. Now hello.
Hi.
So if you actually want to know the correspondence, what you do is that you remove like the one that is 0. There is 0. You say 0.1. Remove 0.1 from 1. What does it give you?
0.9.
0.09. Is it not 0. Because
0.9.
okay, 0.9. Yes, thank you. Now, the opposite, that is, if you do a reciprocal of a number that is greater than 1, then the value will give you is 0 point. If you do the reciprocal of something that is 0 point something, the value will be greater than 1. That's what I want to first of all establish. I don't know if you understand me now.
Yes, sir.
So if the odds ratio or relative risk is less than 1, it means that the exposure is protective. Now, the relative risk or odds ratio that is often reported as a single number with confidence interval. Look at what I just said. The last sentence, not this one, the one I said before. Look at if it is 1. Can you see? If the risk ratio with risk with exposure, if the odds ratio is less than 1, that should the risk with exposure is reduced. If the odds ratio is greater than 1, the risk with the exposure increases. Can you see? If the odds ratio or relative is 1, neither increase or decrease in the risk with the exposure. If the range of confidence interval include 1, then the result is not statistically significant. Let's now look at that one. That one is in the next slide. Look at the confidence interval now. Interpreting confidence interval of ratio. If you look at the one we have done now, okay, maybe we should go back to that. Okay, don't worry. Since I even have a result here. Okay, look at this example now. The one for the second one. Look at confidence interval. Somebody should mute himself. Somebody is disturbing. If the odds ratio is 13.5, look at the odds ratio is 13.5. Look at the confidence interval. It's from 5 point something to 30 something point something. It does not include 1. The same thing with this. Look at what I'm saying. If your confidence interval is everything is less than 1 minus this is the value of your odds ratio or relative risk in the middle. The confidence interval, the lower value will be less than the value, the upper value will be more than the value from this place to this place, and all of them is from 0 point something to 0 point something, less than 1. Then this one, confidence interval, start from less than 1, hence somewhere after 1. This one, confidence interval, start from something and end after 1. But the odds ratio is more than 1. This one, the odds ratio relatively is less than 1. Look at this one. The odds ratio is greater than 1, but the confidence interval and from something after 1 to another thing. So what this one is telling you, this one is significant. These two are not significant. The last one is significant. I want you to ask questions because I want to be sure that you people are not confused. Ask question. from what I just said now. Please ask question. I don't know if you understand. Are people hearing me? Are you people hearing me?
Yes, sir, we are.
Yes, we
Yes.
are.
So I
I
want you to.
understand the concept. So the hello?
What
Hello?
is it?
The last explanation is not very
So,
clear.
Okay, don't worry. What is not clear there? I want to. That's what I want question.
so does the confidence interval,
Hmm.
like I understand, like, okay, once it crosses one, it's not significant.
You don't know the
What I
reason.
want to find out what I wanted to find out is that confidence interval, is it because it's possible that that range, that value can also be a no risk?
Yes. Let me
Is it
just
because of
explain. Professor Waku is like your. I don't know what's from your computer. Something is peeping that is disturbing the voice. I don't know why it's from your computer. I can see it here. Something is affecting the voice from your computer. Now, okay, maybe is it that I pin him? Okay, no problem. There's no problem with our computer, sir. Now, the confidence interval is a range of value. When you estimate, you give your estimate like odd ratio relative risk. Whatever you give is point estimate. It's just one estimate like this, which from your sample is an estimate of the population parameter, which you don't know. But you want to be to certain level, degree of confidence. You want to be confident to certain degree confident that, oh, you can say that the range of value in the population is from this to this. So this one we are doing is 95% confident. We are 95% confident that the range of value in the population will be between this and this. And that range of value will be lower and upper value. The lower value will be less than the value you calculated. The upper value will be more than the value you calculated. So you are trying to say that, okay, this is what I have calculated, but I know that I cannot get what is in the population because I have not studied the whole population as a sample. If there's no way you can actually get the real value in the population from your study unless you study the whole population. But you can say that, okay, it was 95% confident that the value in the population will be in between these two values. That is the confidence interval. Another way of saying is that if they do the study 100 times, in 95% of time, they were able to find the value will be in between, the value they get will be in between these two values. That is what is the confidence interval is saying. Now, about whether it's significant or not is what we are interpreting here. You know, we have already said that if the odd ratio is 1, what does it mean? It means that there's no association between the factor and the exposure and the event and the outcome. Because it means that if it is 1, it means that numerator and denominator, the risk above and the risk below is the same. So that's why the risk is the same from both exposed and not exposed. That is confidence, that is ratio 1. So when you now have a confidence interval that you now give a range of value that include 1, example is 0.2 to 0.8, it did not include 1. But if I say from 0.3 to 4.5, it has included 1. That is, I'm saying that the real value in the population may be anything between 0.3 to 4.5. So it can be 0.3, it can be 0.4, it can be 0.5, it can be 1, it can be 2, it can be 3, up to 4.5. 1 is one of the possible value in that range. And you already know that if the odd ratio is 1, there's no association. So if 1 is one of the value, that shows that it's not significant. So when the range of value crosses that 1, irrespective of what we have gotten before, is not significant. So it creates, what I showed there now is 4 scenarios. A scenario where the odd ratio or relative risk is less than 1 is trying to tell you that exposure is protective. It's less than 1, it's 0 point something. But the confidence interval may range from 0 point something to 0 point something. That shows that it's protective and it's significant. Because if it ranges from 0.2 to 0.9, it didn't cross 1. It means that it's protective, but it's significant. But you can still have the confidence. Another scenario is that the odd ratio is less than 1 also. Yes, it's less than 1, but the confidence interval is from 0 point something to something after 1. Maybe the odd ratio is 0.5 and the confidence interval is 0.2 to 3.4. So the confidence interval has included 1. It's not significant. Though the odd ratio is trying to say that it's protective, but it's not significant. It's just by chance. Then the third scenario is when your odd ratio or relative risk is greater than 1. Maybe you get odd ratio of this one now, 10, 30.5, the one we have gotten. But you now have the confidence interval from 0.8 to 24. In as much that the range 0.8 to 24, it has included 1. It's not significant because in the population, the odd ratio can be 1. That's what it's saying. It's not significant. The fourth scenario is what we have now, where you have your odd ratio 30.5 and the confidence interval is between 3 something to something 50 something. It has not included 1. It's significant. Does it make sense? What I've just said now, does it clarify it?
Yes, sir. Thank you, sir.
So this is the picture I was trying to explain. I don't know if somebody has gotten it now from the explanation. Like this one we have just run now, all is good because the two scenarios are significant. That's why you see the odd ratio and confidence interval, they are greater than 1. But the one I try to reverse is significant also, but the odd ratio and confidence interval are less than 1 is significant also. If it can be protective and significant, it will not be protective, it can be causing the disease and it's significant. But it can show you that it's protective and it's not significant. Once the thing cross 1, it can show you that it's causing the disease, it's not significant. Since those are these two not significant you are seeing here. Please, it's only Ugo that is talking. I want other people to talk because sometimes if you are confused, you are not asking. Nobody, assumption cannot be. I'm not against anybody that asks a question, so I want you to ask question. Even if it is clarification. Because I don't like it when people are just, because you need to know how to interpret it. You can see that the interpretation of confidence interval of ratio, that is, when I say ratio, odd ratio and relative risk, is quite different from the interpretation of confidence interval of the mean, different between mean and different between proportion. Because that one, it is when it crosses 0. Because, when you are looking at different between mean, it means that when you are looking at different between mean, you will minus 1 mean to the other one from the other one. If the mean are the same on both sides, on the two groups, when you reach the mean is 60 and the mean is 60 on both groups, you minus 60 from it, give you 0. So that one, if there's no difference between the two groups, is 0. And that is why the confidence interval, it is when it crosses 0. So when you're talking of difference between mean and proportion, it is when the confidence interval crosses 0 that is not significant. But here, because operation we are doing here, risk, we are saying ratio, we are dividing, it's division. Our operation here is division. It is when two things of the same value you divide them that give you 1. So what we are looking at is where, so when the confidence interval crosses 1, it's not significant. Can you see the difference now? Everybody is sleeping.
Lisa, can you take that explanation?
I understand what you
The one
said,
about
sir. You
mean
said that
and the ratio.
One after the other. Okay.
Oh, sorry.
Okay. Yes, Prof. You say you understand, right?
No, I want you to take the explanation.
I understand your questions, Prof. I want you say you understand, right?
Yes, sir, I understand the one about the odds, the ratio. That is for the risk ratio. Then I know you explained that the one for 0, isn't that for like means?
Okay,
that's what you're doing.
It's the same question Prof is asking now. It's the same question. Just
okay.
The same question Prof is asking. I said that interpreting confidence interval depends on the data you are dealing with. If you are dealing with data that has to do with difference between two proportions, difference between two means, like a t-test, we do is difference between two means. And in my next training now, we'll be looking at means, how to compare comparison mean. We'll be dwelling much on that. that one, because your own difference is measured by subtraction, because x by x1 minus by x2, that is, you will remove one mean to the other from the other. If the mean is 30 here, 45 here, you will remove it. That is, the operation is minus. But here, how do we compare our own risk? We compare risk by dividing. So here is division, there is subtraction. So in division, in this one, whenever there is no difference between the two groups you are dealing with, when you divide both of them, it will give you 1. If the numerator is equal to the denominator, it gives you 1. There, when you are looking at difference between mean, if there is no difference, if no hypothesis is true, there is no difference between the two groups, the mean will be the same. When you now remove it, it gives you 0. Do you get the vision? That is why in interpreting the confidence interval there, with the difference between mean, 0 is what you use if the confidence interval cross 0. If it includes 0, it means that you already know that if the difference is 0, that means that there's no difference between the two groups. That is why 0 is what you use here. There you will see confidence interval from minus something to anything positive. So 0 is the borderline for that one. Whereas here, 1 is the borderline. Here, we don't have negative value in the ratio. It's from 0, no, upward. So the 1 is the boundary, 0 point something. If it crosses 1 to anything greater than 1, we say it's not significant. But there, for that one, if from minus, if it now cross 0 to positive side, we say it's not significant once it includes 0. I don't know if I've answered your question. Prof.
Yeah, yes, sir. It's understood. Thank you,
Yes.
sir.
Yeah.
It's understood. Thank you, sir.
Ugo, I think you have understood this now. Ugo.
Sir, so because I was just trying to clarify the part that you said that the ratio is about, because we're doing division. If it's equal, it will be 1.
Yes.
But for the quantitative, sorry, for the
difference between mean
means,
and proportion. Because you are doing subtraction. If it's equal, it will be 0. If you remove 60 from 60, is it not 0? That one is subtraction.
oh, yeah,
If there are two things, you are looking at difference between two things. When you subtract one from the other, if they are the same, it will give you 0. Here we are dividing. If the two things you are dividing are the same, it gives you 1. That's why 1 is the cross function. There is 0.
Neutral point.
Does it make sense?
Thank you so much.
So any other
Very
question?
well. Thank you.
Any other question? Because this thing, statistics, the branch of mathematics, is just logic. It's not for you to think quantitatively. And let me tell you something. That's the major drawback we have with black man. The black man problem is ability to think. Okay, they are talking of invention, all those going to the moon, everything. The people that is, even what they invented in the laboratory is because they think mathematically. It's a product of thought. When you think logically, you'll be able to bring something out. But here, African man, we prefer enjoyment, party, or anything you can do, maybe artistic word that you just act. As you act, the way you go like that is a fashion. That's we are inclined to bet here. Thinking is a serious business. We don't do it. And that is the major problem we have in our country and Africa with black man. And that's why we need to give ourselves orientation. It's just about thinking. I don't know if there's any further question before we proceed, because there are some things I still want to unravel concerning this odds ratio and confidence interval. Should we proceed?
Excuse me, sir.
Okay, go on. Go on, ma.
From the output for the risk estimate,
okay.
I know someone already tried to ask that already, where we have the odds ratio and then we have the risk estimate for lung cancer in those with the exposure and then lung cancer without the exposure. Does it mean that the two risk estimates now, for us to get the ratio, we would then be, it seems as if it expresses the risk estimate for exposed and not exposed. To get the ratio now.
Okay. I think the way let me just answer the way I will answer it. Okay, let me just answer you, ma. Let me just show the slides. at least show the results. Okay. Then can you say you can use this one, right, Dr. Olagwe? Can you use this one? Can I use this one to explain it?
Yes, please. Yes, it shows the same
So
thing.
you are talking of the second and the last one, the way swabbing like that, right?
Yes, sir. Yes.
Yes. So no, let me give an example. You know, there are some things the study you do, the exposure causes the disease. There are some study you do, the exposure prevent the disease. Like immunization now, the exposure to vaccine, you expect it to prevent the disease. So when if you are doing, maybe this one we just did now, exposure to cigarette, we expect that this exposure is causing the disease. But if you do intervention, maybe we do vaccine or give Imatinics, we expect the exposure to prevent the disease. In that case, when we do our odds ratio or relatively or whatever, when we do our addition, we expect the exposed, the odds ratio to be less. You get a picture to be less. Like for example, if it's immunization we did instead of smoking now, or something to prevent smoking, we expect for that a relative risk. We expect the relative risk to be less than 0, less than 1. But because it's difficult to interpret it, for you to interpret it, you have to now calculate the what do I call it, reciprocal. Because if it is less, if it's more, now if it is like for this one now, it is clear that the people that are exposed to cigarettes, the relative risk is 8.143. They are 8 times more likely to have lung cancer than the people that are not exposed. You get it now. But if, let's say, is immunization, the result it will give us is this one, 0.603. The same data will give you that result as the relatively that are the people that are immunized, that are exposed. The relative risk is that is there is 0.6 times. The 0.6 times means it's less than 1. It means that it's protective, but it's difficult to interpret. So what you can do is to calculate the reciprocal you use to interpret it. So that is why this one is giving us the result like that. That is why the intelligent people that advise these people that are doing the program, let's do the other way. So if I'm doing it now, I just run it, I know what it means by looking at this what do I call it? 0.6, 1 divided by 0.603. No, you first of all remove that 0.603. What did you disturb me? So somehow you remove. Okay, I wanted to calculate something. Somebody is just disturbing me. Somebody should do. You can do the reciprocal of 0.8.1. 1 is 1 divided by 8.143. So there's a way where you can exchange the two together. So what this one is just giving us is that it's giving you 6 scenarios. It may be that you are trying to see if this intervention is protective or intervention is causing it. It gives you the result. So you choose one you want. Most of the time, this type of result is more useful whenever the way it has given you now is very useful. Whenever what maybe that particular thing turned out.
I can't hear you.
You cannot hear me. Is it my internet? Wait. But my internet. Can anybody hear? Can any other person hear?
We can hear you.
But see, you cannot hear me. If you cannot hear me, maybe it's from your hand.
I can hear, sir.
I can hear you.
So the essence of giving that two result is just in a situation where maybe the thing now turn out to be something like 0 point something, so that you know how to interpret it. You can use the reciprocal. Like now, if it were to be that the odd ratio for this one relatively is 0.6 something, and it has already given you all the reciprocal to be 8 point something, instead of saying that these people are less likely, I will tell you that they are 8 times less likely. Instead of saying more likely, less likely to have lung cancer. I don't know if you understand me, man. Dr. Olagunjoye, is he out? Dr. Olagunjoye, unmute yourself if you want to. I'm not hearing you unless you unmute yourself. Dr. Olagunjoye, I think it's our hand that is something that is machine that is causing the problem. Any other comment or any other question?
So I noticed that in the output box for
Yes.
SPSS, you know, you did that when you were doing that, you know, the non-exposed over the exposed. Of course, the no came first, if you remember, before the yes in that output table. But I noticed that first one of the odds ratio was still remained the same. It still had the name, the yes over no. That's
Yes.
I was thinking that maybe over yes.
Because the odd ratio, if you look at it, it will not change. In that sense, you examine that. So that's the one they reprogram there is the relatively the explorer to give you that What they change there is what they just is the risk they target for you to know. You examine is the risk they want to explain there. They want to see the way the risk vary between the two methods. Yes, that's why it's because of the way they program it. It's programming. It's programming. And another thing is that even some of these software, that's why they keep on developing. The users also make their comment. Why not do this one? When they send the comment to them, most of them. Dr. Lanzo is still saying that cannot hear me, but everybody is hearing me.
Also, did you mute her on your own side?
How can I mute her? I didn't mute her. I cannot mute anybody. I didn't mute anybody. I can only remove. There's no provision for me to mute you because I allow you to. I can only remove somebody. I can only even ask you to unmute. Dr. Olagunjoye.
It's a network.
It's a network.
Join again. He wants to leave and join again.
Okay. That's what his chat. He sent chat to me. Let me reply because I don't know. So any other question? Okay, she's even. I think she has even gone out also. Maybe she's trying to rejoin. She has gone out. She has gone out. Any other question, please, before we proceed? No question? Okay, let's continue. Let's continue. Hope she will join very soon. Let me just send a message that okay, let's continue. Let me go. I want to explain something. There are some things that I want you to get to understand. Now, I think we have thrashed out this area. Now, what I want you to look at when the probability of an event happening is real, odds ratio and probability are close. I think I've said it. When the disease is real, that is when the risk or probability is very small, the odds is close to the risk. So it's the same thing. The odds ratio is close to relative risk when the disease is real. This is because A is much, look at the, if you remember the formula for all the relative risk, is A all over A plus B, everything all over C plus D. You remember that. So when the disease is rare, you know, is 2 by 2 contingency table. A is the occurrence of the disease. So when you say A plus B, A is extremely small compared with B. That's what he's saying. That is, the people that have disease is A. They are extremely, among the exposed, they are extremely small compared with the people that don't have the disease, which is B. So you can as well say that A all over A plus B approximate A all over B, because A is extremely small compared. We can just say, let's forget about A is not in the small. It become right only B there. It approximates A over B. The same thing among the non-exposed, because the disease is rare in the population. The C, which have the disease among the exposed, and the D, we don't have the disease. C is small, extremely small compared with D. You can as well say that, let's write out D in C. You now write it as C all over D. Please, somebody is. Where I log out is that somebody is disturbing. I don't know. Somebody's computer is echoing my business. It's like, is it? I don't know whose computer. Okay, it's no more doing that now. Please. Yes, what I was saying. So when you now put it now, A all over B divided by C all over D, if you remember, you change your subject. Okay, let me, maybe I should share, because sometimes, what I was saying, A like this, all over A plus B, that's plus. We approximate, that is, approximate A all over B. Because this A is small compared with B. So you can just neglect it. Because A is the people that have the disease, B, people that don't have the, because disease here is rare. For C over C plus D, you can say it approximates C all over D, because C is small compared with D. And you know that the relative risk is this, A all over A plus B everything all over C plus D. C plus D, yes. So it will, this one now we approximate based on what we just said now. It will approximate A all over B, everything all over C all over D. C all over D. And is equal to A over B times, it will become D, you remember your mathematics, all over C. And is that is AD over BC. Is that not the formula for odd ratio? Yes, that is the formula. This we started with relative risk. This formula for relative. When the disease is rare, so it will change to equal to formula for odd ratio. So when the disease is rare, odd ratio approximate relative risk. And then if you remember when we talk about concept of risk and odd at the ab initio at the beginning, I said that when the disease is there, even the odd is close to the risk. We said it now. If the risk is 0, odd is 0. If the risk is as it's increasing, If the risk is 0.1, odd will be 0.1 something. Something will be added to it. When the risk is 0.5, odd is 1. So what it's telling you is that if the risk is small, the value of the odd is close to that of the risk. And you know, when the risk increase from 0.5 to 1, the odd increase to infinity. So if the risk is the probability of the event of the disease. So when the disease is rare, the same thing, the odd ratio will be close to relative risk in your calculation. I don't know, it's very clear. And that is why it is appropriate when the disease is rare, is appropriate to even do the study that will require you to calculate relative odd ratio, like case control study, cross-sectional study. Because, like, for example, now, if you want to do, maybe you say you wanted to know if a particular thing causes a particular, like maybe women taking OCP, if they have varicosity. So if you want to do core study that you will calculate risk over time, you may follow up many women. At the end of the day, I don't know if this is anyway, I'm just giving an example. You follow many women for 5 years, 10 years, you will not see appreciable number that develop varicose vein if the thing is rare. So at the end of the day, you may waste money. You can even do 40 years and you are following or you are spending money, because following up means that you have to trace those people and still go and assess them if they have developed. You keep on doing year by year, year by year. So for you to trace them, you have to give them, spend money to trace them, to take measurement, to do the survey, and even give them money to come for them to even be responding to you anyway. You have to give them. So at the end of the day, core study is the most expensive study. It's more expensive than experimental design. But if the disease is real, you can actually look for the people that, because there's a risk of you doing the core study, still you wait for so you don't even get anybody that is. So you can, if the disease is real, you can actually look for people that have developed it. That's why many people do multiple center study. Like in Nigeria, now you okay, how many you have in ABU, how many you have in Enugu, how many in Ife, how many in Ibadan, how many in Calabar, how many in Kamaduguri. You begin to look for two cases, one case by center, before you can even gather 20 in the whole country. You now do case control. You now have the history of exposure, that is case control, and you will now calculate odd ratio. But the beauty of it is that if the disease is rare, what you get is close to what you will have gotten if you are calculated, spend money to do a cohort study. I don't know if it's making sense now. So when the disease is rare, the value of the odd ratio approximates the relative risk. So in that situation, you can even do case control study, and since the disease is rare, what you get will be what you have got. You will get if you have spent much money to do core study. I don't know if there's any question concerning that. Any question concerning that before we move to the next concept I want to explain? I don't like it when people are self-motivated.
Thank you, sir.
Yeah, I don't know if Dr. Olagwe has not joined. Join back. So it's well understood, right? We should proceed.
Yes, sir, it's quite clear.
Okay, that's great. Now, other things. So you just like what I've just said on this table now, that's what it's actually showing. You will see that if the probability P1 is the exposed, non-exposed rather, P2 is the exposed. When you look at it now, look at in this case now, you can even see the relative risk is the same across. But in this case, the number one, the disease is rarer than the other one. Yes, I'm not. In this number one, the disease is rare, followed by so the disease is higher here. It's 70% here and 35%. 35% here, 5%, 25%. But you see the relative risk is constant as the something is increasing. That is the relationship between the, that shows that the disease, if it's increasing, is increasing in both exposed and non-exposed. That's what it's saying. The relative risk, but you will see that the odds ratio is small, is closer to the relative risk when the disease is rare here. Can you see? 2.11. Here is 2.42. Here is 3. Here is 4. So as the disease increases, the odds ratio, the value is far away from the relative risk. But if the disease is rare, the odds ratio is close to the relative risk. That is why if the disease is very common, is a poor, if you go and do case control instead of cohort study, the case, what you get in case control is really odds ratio is far from the, it may be far from the real burden of the disease. And that is why anyway, at the end of this, you're going to see a formula that converts odds ratio to relative risk. Because most of the meta-analysis, when you do meta-analysis, because most of the study report relative odds ratio because it is easier to do, it's cheaper to do. So most study, even whether the disease is rare or not rare, they report odds ratio because they do a simpler study that does not, it's not costly. Simple is not in the sense of how to carry it out, is by the money you spend. So a cheaper study, let me call it cheaper study, case control study is cheaper. So you see that most of the published literature concerning a particular problem is odds ratio, either close to a case control or descriptive study. You will see when they now do meta-analysis, most of it is quoted because most of the result is in odds ratio. So that's why most of what they present in meta-analysis also is odds ratio. So the issue there is that once the disease, body of disease is not here, is high. The value of that, when you get odds ratio, it may be far from the real burden of the disease. So I think we did that one. I proceed. The other thing I want you to get to know. Now, this graph is showing the relationship between relative risk and odds ratio. When the events occur equally in both exposed and non-exposed, or we have already said that the relative risk is 1 or the odds ratio will be 1 also. You know, are you following? If the risk of a particular disease is the same among the exposed and not exposed, that shows that the relative risk will be 1 and the odds ratio will be 1. So that's when the relative risk and odds ratio is the same. When the risk is the same in both exposed and unexposed, or the risk of an event is the same in both exposed and unexposed, the odds ratio equal relative risk and they're equal to 1. But then 1. Look at the diagonal of this graph, because this graph is plotting odds ratio vertical, relative risk ratio, which is relative risk. No, I've already told you the both of them are ratio. Odds ratio, that's a very good one, risk ratio. Now, look at it. When odds ratio is 1 here, that's when relative risk is 1. Look at where they cross. Can you see here? The middle. Relative risk is 1. If relative risk is 1, odds ratio will be 1. If relative risk is 1, odds ratio will be 1. And it's only in the situation when the burden of the disease is the same in both the exposed and non-exposed. Now, if as the burden of the disease increases, look at this blue. So this first one now, this is where the graph, this black line, this is where the disease is the diagonal. Because if you look at this graph as a square now, the middle is the diagonal. Now, and it's angle 45 degrees. Now, as the body increases small like now, if the body increases in the positive direction, it not actually increase. If the thing is either is the factor is causing the disease or is protective, whichever way. Like now, if the thing is up here, this blue line, it shows that it has increased small. This one here, the blue line here, that is below, when they are below 1. It means that this factor down here is protective. This factor up here is causing it. This one is causing it. This green here is protective. I want you to notice something. When the odd ratio, when we said that when both of them they are 1-1, when the factor concern has nothing to do with the disease. Is there any question? So look at the reference. If you still look at the key here, reference risk. Reference means the burden of the disease in the population, or the burden of the event in the population. So when the risk is just 10%, okay, I will explain something like before I come to explain that. When the odd ratio, or both of them, they are greater than, what's this? They are greater than 1. Can you see now? Above, can you see now? Above, greater than 1. The relative risk, the odd ratio is greater than relative risk. Can you see now? This side of the graph now, look at this point, 22.5, relative risk of 2.5. If you follow up to this graph, blue graph, you will see that it's above, it's above 2.5 for odd ratio. Can you see? When both of them, they are greater than 1, when odd ratio and relatively are greater than 1, the odd ratio is greater than relative risk. Okay, let me put it this way. When relative risk is greater than 1, the corresponding odd ratio for that data is greater than relative risk. Can you see now? Under 2.5 here now, look at each of these graphs. Look at even the green one. When you look at 2.5, look at, and the greater the burden of the disease, the greater the difference, the odd ratio will be greater than the relative risk. Now, when the odd relative risk is less than 1, like look at it now, less than 1, the corresponding odd ratio is less than relative risk. Look at it. Look at this one, 0.5. Let's look at this graph now, this red one. If this is 0.5, look at where it joined the event. Can you see the odd ratio is less than 0.5? I don't know if you can get this sentence now. When relative risk is greater than 1, the corresponding odd ratio is greater than relative risk. When relative risk is less than 1, the corresponding odd ratio is less than relative risk. And the reason is very simple. The relative risk, the margin, the span is very narrow, but the value, because it can be from 0 to something, but the other one, odd ratio is from 0 to infinity. And that one, you can see it on this graph. You will see this vertical axis is for odd ratio. This horizontal axis for relative risk. You can see this graph now, the way it's turning. None of them, you cannot turn to this side. So they cannot turn to pierce, the graphs cannot pierce this side or this side. They can clear the upper and this thing, because this one is along the vertical. Can you see now? The odd ratio is along the vertical, because the odd ratio is from, though it will not pierce this one, it cannot be, though it will end at 0 here, but the upper part, it can go to infinity. So the range of the value of odd ratio is from 0 to infinity, just like the way the range of value of odd is from 0 to infinity. But the range of value of of risk is from 0 to 1. But for odd ratio, is from 0 to not actually 1. It can be greater than 1, but it's not to infinity. It's narrower. So it's like on this side, positive side, the corresponding odd ratio is higher than relative risk. To the right side, more rightward than relative risk. On the negative side, the corresponding odd ratio is less than relative risk. Is less than relative risk. That is to the left also, range of value. I don't know if there's any clarification concerning that. Any clarification? Nobody's answering. It may mean
Thank you, sir. I understand it, sir.
It's
okay.
clear.
It's very clear. Everybody, plus if it's not clear, you can talk. Let me just see the any chat.
It's quite clear, sir.
Very clear. Dr. Olagunde has not come back. Okay, he has come back. Dr. Olagunde, unmute yourself and talk.
I'm here. I'm following. I'm with you.
Yes, you logged out. I sent it to you that you. I think it was your computer. It was because everybody
Yes, I
was
think
hearing
so.
me. Yes.
I think so. So I found
Any question because you might have missed out something. Do you get what I just said last time?
Yes, I did.
Because I want people to understand. Because those are the logical. Once you understand very well, no computer is garbage in, garbage out. It's you that know what you want. That is why, let me tell you, you need to, nobody, if you are very sound in your statistics, nobody can just play you around. Nobody can play you around. If you are sound, understanding, and knowing your statistics is even more important than knowing how to use machine to analyze it. Knowing how to, it's an addition. It's good. It's an addition. So understanding it is the most important thing. Prof, Wako, you have a question?
No. I just concur with you.
Okay, thank you, sir. So let me go back. So, Dr. Okay, so if you have understood that, I think we proceed. We proceed.
There's exam tomorrow. Since you have read.
Okay. Somebody is talking. You can mute yourself if you are talking. Now, the last week, Professor Uwakwe was here. He was asking me if there's any formula that convert odd ratio to relative risk, whatever. Yes. This is something. So where the PO is the sample probability of the outcome. The PO is what they wrote as a reference risk. That is the risk of that thing in the population. That is the prevalence of the event in the population is the reference risk. The prevalence of it. So this is how to convert, because the reason people do this is that most of the research work is in odd ratio because it's cheaper. So you search literature, even meta-analysis, most of them are in odd ratio. So that's why some intelligent people, and whenever, especially if the body of disease is high, the risk estimate is far from the reality. The risk estimate, the odd ratio will give you be far from the reality. And it's not good for economic analysis. No, it's about money. If you want to quantify how much we spend on this, so intelligence men are okay. They now try to get this formula, look at the relation between them, so that if you, even though these things are reported in odd ratio, how do we know the corresponding risk? Of course, this corresponding risk will be smaller because the odd ratio try to overestimate the risk. Whereas when you now change it to relative risk, we're able to give you the actual risk. So I don't know. Now, the last thing I want to discuss, if there's no question, is to talk about the criteria for judging association.
Please, I didn't get that last explanation. The one about the last one you mentioned about how you can convert OR to R. If you can just.
Can you see the screen? Can you see the screen?
Yes, sir. I can see it. Yes, sir.
That's it now. Our relative risk equal to odd ratio over 1 plus PO times odd ratio. Very simple. PO is the prevalence of the disease population.
Okay. Then you were saying, okay, you said that, is that the same thing as the reference risk?
Yes, that's the reference, yes. Or some people call it baseline. Baseline risk, reference risk, the same.
Okay. So it's the prevalence of the disease in the population.
Yes.
Okay, thank you, sir.
So since why they did that is that since most of the publication, what you are interested in is the risk, the relative risk. That is the risk among the exposed divided by the risk not exposed. It's not actually the odds ratio. You examine now, but the odds ratio usually overestimate it. It gives you a bigger picture than it is. It's like a over exaggerate. So if you actually want to know, especially if went for economic analysis, when it comes to money, we want to actually quantify. We want to know for economic analysis of a project of health program. We actually want to know the actual risk of the burden of the disease. So you can now convert the odds ratio to relative risk. That's why some intelligent people like Zhang Ju invented this. So let's quickly look at if there's no other question, criteria for judging association. You will see that when we did all our chi-square, all those gist one, we said that just telling us that something significant does not mean anything. But that method is what we call hypothesis testing. This method of measure of association with confidence interval is what we call confidence interval. So what we have done today is we are actually if you look at it, even this one, so you can calculate the chi-square, whatever it will give you. That is all those on the hypothesis testing. What we have done today is confidence interval. In the confidence interval now, you will notice I'm just trying to I've not started talking about the judging association. I just remember something about this confidence interval of a team. If you want to publish in Lancet now, all those correct journals, nobody take p-value from you. All these guys correct p-value, nobody take it from you. They want you to give them confidence interval. They said that these things started in early 19s, when it started with industrial research, where they dichotomize study into significant and not significant. It says it has no place in medicine. So they will prefer you talking about confidence interval because the p-value give you only one information. Confidence interval give you the same information with additional 2 information. So p-value confidence interval give 3-fold information, while p-value give 1. What p-value give you is significant, is not significant. Is statistically significant or not? That's the information. There's a difference, no statistically different, there's statistically significant different. That's all. But the confidence interval quantify the different, the measure of association, like this relative risk odds ratio. It quantifies the association one. It also tell you the range of value, because what you are able to get is what you have in your sample. It's able to give you a range of value within which you can find the population value with a level of confidence. That's the confidence interval for you, it's lower and upper. And also tell you if it's significant or not, which we have already interpreted with this picture here. So can you see? And that is why confidence interval is preferred over p-value. But it's a pity here that many people sometimes when they even do people cannot interpret confidence interval. If you do your work now, if you put confidence interval, there's no point for you to put p-value. But many people, they don't, since they cannot interpret confidence interval, they want you to see p-value. But let me tell you, if it's statistically significant with confidence interval, it will be significant with p-value. Both of them, they work together. There's no problem. But the only that the confidence interval give you more information than say it's significant or not. It's able to quantify it and give you a range of value within which you can find the population value. So I think I just clarified that. Let's go to the last thing I wanted to say. So having said that, you now know that even by you quantifying association does not mean that it means causation. But the fact you say that this thing, oh, I can see that this is my odds ratio and confidence interval. It must be this OCP that is causing varicose vein, or it must be this cigarette that is causing cancer. It doesn't mean that. You have to merge it. Statistical significance does not mean clinical significance or mean risk significant. Even there are some things that are not even related. You can put your statistics, it will be significant. It may be because they are not related, but both each of them are related to something else. And that is what is, it's just like if I go now, I visit Dr. Olagundoye, and I met somebody, a friend there. Because the friend, I don't have any, me and that friend, we don't have anything in common. That person I met there, I don't know, the person doesn't know me. But both of us all now have one person in common. It's Dr. Olagundoye. So in that case now, that Dr. Olagundoye is the confounder, is the person who, when they now say, oh, I saw you with Mr. or Mrs. So-and-so. It's not me. I came to see somebody and that person came to see that person. Do you see it now? So sometimes you may see that there's association between both of them. It may not mean there's association. It may be something else, underlying another thing that is confounding for it. Now, to judge your association, this criteria was developed by one man, according to the name, in England. And they are arranged according to importance. The number one is the most important. The last one is the least important. Temporal sequence, number one. Temporal sequence means that that exposure, that factor you think is causing the outcome, exposure must precede outcome. That person must be exposed before the outcome happens, before you can see that thing is causing it. It's just like when you say obesity causes hypertension. It's possible somebody was hypertensive before he became obese. Maybe after he has hypertension, he now begin to have problems, he now became depressed and now have obesity. So in that case, does obesity cause that? No. So before you can say a factor cause an outcome, there must be temporal sequence. That temporal sequence means that exposure must precede outcome. That's the most important thing, number one. And that is the drawback of this other study, anything that is not prospect or the case control, and a cross-sectional study, not case control, because case control somehow is a longitudinal study also, even though it's a retrospective. But that's the drawback of cross-sectional study. There's no temporal sequence. You cannot establish that because let's say this issue of obesity and hypertension now, you just go to the community, you say you are doing a survey. You want to see the relationship between obesity and hypertension. It's the same day you measure somebody's weight and height and the blood pressure and confirm also that, oh this man is hypertensive. And do the weight, height, BMI, say, oh, he's obese. Because you will not know which one comes first between obesity and hypertension. In your study cannot establish temporal sequence. It's different from somebody that started with people that were obese and people that are not obese and none of them is hypertensive at ab initio, and begin to follow up to see how many people will develop hypertension in between the two of them. By the time we analyze later how many after some years, and now discover, oh, more of the people that are obese develop hypertension. You can also, oh, obesity contributes to hypertension. So temporal sequence. So in establishing temporal sequence, also your study design will help. That is where the study design matter. So that is why people usually say that for causation, to establish causation and effectiveness of study, experimental design is the gold standard. But it doesn't really mean that experimental design is the most rigorous. No, it doesn't mean that it's the best. But for the type of design depends on the state of the problem. I think we'll talk about that later because there's something that is related to that. So just know that temporal sequence is the most important, followed by the strength of association. The strength of association, when you say either you are talking of the relative risk of odd ratio, what is the value? If something is 10 and something is 50, there's a difference. The 50 is stronger than 10. If you say, oh, people that have this are 10 times more likely, and say people that have them 2 times more likely, the 10 times more likely is stronger because it's the strength of association. So if the strength is higher, if you do many something factors, and one has the strength with one is higher than the other, that one is more factor that's causing that problem than the other one that has smaller one. Can you see number 2? Number 3, consistency of the association. As the work be done many times by many people, like for example now, the use of evidence for using low dose aspirin for prevention of death from cardiovascular disease have been confirmed by many clinical trial, randomized control trial, many. And when you do meta-analysis, it gives you a lot of study that have been done to confirm that. That is consistency of the association. Then the next one is biological gradient, dose-response relation. You know, when we say that, okay, temporal sequence, then we talk about cells of association, then you see people that are exposed more, are they more likely? Because if you try to grade the exposure also, some people may be exposed more. Maybe you tell the day, maybe they like cigarette now, the amount smoke, the length of time the person smoked in the past, those are dose response. If the probability is higher, the risk is higher, you calculate the risk is higher among the people that have exposed for so long or take more of it. That is dose response relation. Now, specificity of association. Does the exposure lead only to the outcome? You see, in this one now, in the situation where you only attack, like maybe they say tuberculosis bacilli is the only one that is causing, is specific, causing tuberculosis. They have not found another thing to be causing tuberculosis. Plasmodium is the one causing malaria. They have not found another organism that causes malaria. So it's specificity of the association. So, but if you look at it, it has been arranged another other important. It's not the most important because it's possible that for the fact that something can be causing something and can cause another thing. The malaria, okay, what I'm actually saying here is that that particular thing, that's the only thing that is causing a specificity of the association. Like by malaria plasmodium, it has not been found to cause another thing. Like now, when we say mosquito now, mosquito is not only malaria it transmits, it can transmit other things. But the disease that is causing, the agent that is causing malaria is only causing malaria. Does it cause other things? So if it's the only thing it's causing, yes, it's pointing to it. Then biological plausibility. Does it make sense? Biological sense. You know, you as a clinician, when they just run the analysis, you just see, you don't just take it like that. You have to look at, does it make clinical sense? Does it make, can you explain it? It's part of it. But if you look at it, it's number 6. It's not as important as the first 5. Because something may not make sense doesn't mean that it cannot work. It's just like when law of relativity, when Albert Einstein, first of all, proposed the law of relativity. He shook scientific foundation, scientific society to its foundation. People, no, they say nonsense. The great physicists and many great scientists were saying nonsense. But they discovered it was true. It was like a dream. So something may not even make sense. It doesn't mean that it cannot bet. Somehow, it's part of it. That's why it's not number 1. Look at public health. Most of the things we do in public health does not make sense. Don't make sense rather. Before the germ theory, public health has been there. Before the germ theory of disease, people discovered that if the clay is around it is clean, they discovered that people will have less disease. But they didn't know that what they are cleaning is to prevent the germ from making contact with human being. So possibility. Sometimes you may not be able to explain things, maybe not, but later you get to know. They're coherent with existing knowledge. Is it consistent? If you look at from this specificity, biological possibility, coherent with existing knowledge now, they are becoming less important because that's why they are down, because some of them are challenged, even though you use it, but somebody may say something, doesn't, just like the one I told you about, the public health and this thing. When those things came out, it was not, the people could not place it. How does it? It's just like the issue of miracle. Scientifically, you cannot prove miracle. But for the fact that you cannot prove miracle does not mean miracle does not happen. It's only that you cannot prove it. It doesn't mean that you cannot just prove it. If you prove it, yes, you can say it happened. If you cannot prove it, it doesn't mean that it doesn't happen. It may mean that you don't have what it takes to prove it. So, coherent with existing knowledge, something may not be coherent, but though it's part of what you look at. It just all those things that just red flag. That okay, if it raise a red flag, you look at it very well. The experimental evidence, as randomized control trial be done. If you look at this one now, is number 8. It's one of the least important. Because here, what I was saying before when I started talking about temporal sequence, and that's I will say it later, is here about experimental design. Some people just carry this experimental design as if it's this. As far as I'm concerned, it's rubbish they are doing. Apology. Most of our people, when they are going for an exam, they say that if somebody did experimental design, is likely to have distinction. So they say they don't want observational study or descriptive study. It must be experimental. But the funniest thing is that you cannot perform. There are situations where you cannot perform experiment. Experiment is easier in some situations. It's not even easy to perform experiment with human being. Okay, like now if you want to test the effectiveness of vaccine, well, you can perform experiment. Even that one also, ethical issues. Those people that you cannot really prevent, you cannot deprive some people the vaccine if you know that it works. So if you know that you are still testing it, you subject people to experiment. The people that were in control, if it works eventually, you must go back and do it for them. But when you cannot, that's his treatment now. But in disease, you cannot afflict people with disease. I say, I want to give this secret. A factor of disease. You know that I can cause disease. I say, I want you to smoke this pack of cigarette for 20 years. Smoking will come and receive you develop lung cancer. And you will give some, you don't give them. Which type of experiment? So for ethical disease. So there are some experiments you cannot do. So when it comes to our own public health, the experiment in life is the effect of education. They have analyzed a lot of their projects. Is they tell lie? When by the time they finish analyzing the thing didn't work, they change the figure. Many people give data, they say they want to change. I say, you want to tell lie with statistics? He asked me to do this. I can tell you all the experimental design I've analyzed, all these effects of education, they are all rubbish, I'm telling you. Because I see like all of them tell. The thing is not, and because if they go and report that thing, they say, that shows that they will fail them. That shows that your experiment, your work is nonsense, it's useless, all the effort is useless. To prevent that, they change figure. They change figure and now come and tell you that the education is effective. But to me, negative finding is finding. If you do education, you do it rigorously, you explain how you did it, all everything. If it doesn't change, you say it doesn't change. I don't know why somebody should fail because of that. If I look at the rigor of your this, I assess your work, I pass you. That is your finding. But here, it has to change. And they are saying that this, and you know, in experiment, one thing is that at the design stage, you control for confounder a lot in experiment. But there are some situations where if you cannot perform experiment observational study, you cannot control for confounder at the design. You can only control for when you're analyzing. So you see that it does not make experimental design more rigorous. In fact, there are some observational results that are more rigorous. In even in collecting the data, you try to control for in collecting your data, all those being triggered in the way you scale you use and the type of training you do, just to make your data to be more accurate. You discover that they are more. So the rigor, the ease of the experiment has nothing to do with the just study design. So there are a lot of issues around that. This example I gave about randomized control trial confirming or establishing the fact that low dose aspirin will prevent death from cardiovascular disease. That was what was found, and they started prescribing low dose aspirin until another study discovered that many more people are even died from bleeding because of the aspirin than they will have died from the heart disease. So that showed that after they have done the experimental design, which is because experimental design actually does not look at the most of that. It doesn't look at the effectiveness. It look at the efficacy because it's look at the effect in an ideal situation, which does not actually happen because a lot of pregnant women are excluded, epilepsy excluded, sickle cell excluded, this one excluded many things before. Exclusion criteria plenty. At the end of the day, they now say this is the result. But in real life, pregnant women will still have that problem you are talking about. Epilepsy person we have, diabetes we have. So when they take the treatment, what does happen to them? So that was what happened to that one. If you do experimental design to establish a treatment, as you are giving the treatment, you are supposed to do an observational study to follow up, which is even more difficult. Is even more difficult to do in the community. To now to follow up people that are using that treatment is more costly and more difficult to do than the experimental design. So to me, the study design is a function of problem. The appropriate study design depends on the level of the problem in the society. When we had the first case of HIV was in 1986 in a 60-year-old girl in Lagos. I'm sure the person that got that do case report that attend to that girl would do. In fact, maybe we will have gone to Geneva to present case report or just one person. Because you cannot be saying you are doing experimental design for because it just even you cannot even do descriptive study because the thing had just come. The problem was new. Later, when we have many cases, you can do 2 or 3, 4, 5, 10 cases case series. When it became common, you cannot do cross-sectional study where you say, okay, KAP, this. It is when you have learned much from the KAP, you can okay, the effect of counseling, you cannot do experimental design. So when you are designing your study, the best way is to question the problem when you establish the problem first. What is the best design with the state of this problem? If it's an area where not much has been done before, it's a new thing, new problem, you cannot even go and do experimental design. You cannot do all those there. You have to start with some descriptive study because descriptive study generates hypothesis. Then analytical study test hypothesis. Can you see the gradient? So all this, anybody that is examiner, don't say that somebody you must be. So it's here in Africa that you force people to look for a way to solve problem. And now when you now look for this is the way to solve a problem, you are now looking for problem that thing can solve. No, you should identify problem first. Then what is the best way to solve the problem? So when you conceptualize your study, you do your literature. Is that one that inform the study design for that problem? Then the last one is analogy. That is the association similar to others? If other work has been done, is it similar? So that is just it. And I don't know if any question. I think we end any question before. Any question or comment? Oh, people are not sleeping because I've talked extensively and.
No, sir. No.
Yeah.
Like you made very, very valid points. Because I was even trying to, because I thought, I know that yes, people always tying, everything has to be experimental for it to be credible, and it's usually giving value. And
yes.
Like you said, with exams and everything.
I can tell you somebody I analyzed for in your department. The examiner, the lady has traveled now. Is absolute rubbish, and she has decision. Absolute, the whole work they call experimental design, all the lies he told. And after I did the right thing, what he collected is because I made a mistake, the padding that they did together with the supervisor. And they say, yeah, and say she has decision. Nonsense. Let's continue. Go on.
Thank you, sir.
Yeah, welcome.
Yeah, this the list of criteria now, it's like a paradigm shift somewhat, because the reason why people tend to favor experimental design is because of this hierarchy of evidence, where we say it should be the meta-analysis, the systematic review, the randomized control trials, which are basically the experiments. But I see now that in this criteria, maybe if this criteria becomes maybe global and it replaces that hierarchy of evidence, where the meta-analysis, systematic review, and the randomized control trials are seen as superior to the cohort, the case control, and the other observational study designs. Now gains more credence. Maybe it would make a difference, because I see that number 3, which is supposed to be consistency of association that we get from meta-analysis, it used to be number 1 in that criteria. So I'm wondering, this criteria, what is the source and how well accepted is it?
Oh, this one has been this criteria is only if you check the name of the person is in the module. If you the module, okay, I think I put in the website under measures of association. If you check it, I can check it for you. The name of a Greek, no, I forgot the name. I actually remember it. It has been there. It's in the public health book. I got it from. It has been there. So let me just clarify what George just said there. We are not, when they say evidence, yes, experimental design give the best evidence. The reason being that from the design, you try to remove a lot of confounder, right? What we are saying is that experimental design is not more rigorous. That if somebody did experimental design, does not mean that it has done more work than the person that did not experimental design. Then the way to solve problem in society is not by looking for the design first. It's by looking, when you do your literature, you know there are some problems that are new. It's the state phase of that problem that will determine how we solve it. It's just like somebody did surgery now. If the type of treatment they give depends on, even if it's the same problem, the stage of the disease, like if it's somebody is having fibroid now. So if it's just small, like they know what okay, this is what we should do. If it's this one, this is what we should do. If it's if it's not giving you problem, leave it. If it's now pressing on something causing problem, let's remove the womb. If the person is no more giving birth, he's not going to use the womb again. If the person is going to use the womb, if it's causing problem, they will not remove the womb. They remove the fibroid. Can you see now? So it depends on the problem. But not that say, oh, the gold standard for the treatment of fibroid is total abdominal hysterectomy. No, it doesn't make sense. So what we are saying is that per time, whenever you do your literature review, there's a best for that level of that evidence you have for that particular problem from literature. The study design, it should be based on what the problem, what you have for that. For example, now when they do randomized controls trial for aspirin, they were giving people aspirin. They didn't bother to be studying those people that are taking the aspirin, and people were dying from bleeding. You get it better. And to even do that one, it even cost you more money and more rigorous than the experimental design they did in giving people drug. And when you give the experimental design, what you are actually doing, you are not even looking at the effectiveness. You are looking at the effect in this situation, which is a efficacy. Because there you have to remove a lot of confounder. This one do not take, this one should not be part of it. But in the real life, the person that will take it will have some of those comorbidities with them. So that is why when you push a particular drug or treatment or evidence to the population, you must, and they start using that thing, you must follow. So study this is a circle. So that one we pose another research question. What is the effect of this? You need to study it also. You need to do observational on them. That's what I'm just saying. I'm confirming to you, because let me tell you, man, even as a resident doctor, I analyzed over 400 projects. Professor Klokide will confirm what I'm saying. I analyzed over 400 projects, even as a resident doctor before I finished my residency. And after that, I analyzed master's, fellowship, PhD, many things. So I know what I'm saying. So a lot of people just, I'm telling you, all the experimental design, especially in public health, all those effects of education, all the ones I've handled, all of them tell lie one way or the other. And they even tell, I said, I cannot do that, they go and fabricate. And some of them come and they say they have the best, this, because the people that are examining, they have already made up their mind that anybody that just do experimental, if it's first of, they have already given some mark. That I've said that is absolute nonsense, and that is what is happening in Africa. Because the people look at, they want you to say, okay, this is what I want to do, solution I want to provide. The solution is based on the problem on ground. So that's what I'm just saying. I'm not saying that it gives the best, it has the best evidence because you remove confounders from it. But there are some situations also where you cannot help it, you cannot do experimental design. There are some situations. So why should somebody be looking for, you want to do research and say, I'm looking for effect, because in our own palace is effect of counseling or effect of education. I'm looking, okay, which effect will I do now, which effect? Instead of you to recognize, identify area of problem, maybe area of interest and problem, and do literature review, and then see a research question. Then research question, then what is the best study design? That is the way a researcher, people that want to make progress, that's the way they think. It's not the other way around. Thank you, ma'am. Any other one?
Thank you.
Oh, yes, ma'am. Yeah. Any other comment? Is it that because I see that it's the senior one that now responded now, the junior one that not say that they are confused?
Sorry, sir, we are not confused. Okay. Sorry, at a point my system went off, so I was no longer with you, but I was trying to catch up.
Okay. It's like Dr. Emebe Chebe has a question. Your decision was popping up.
Okay, no question per se. It's just I think what you've done so far is quite clear. This part is the way you've outlined it to me is quite straightforward. I don't particularly have any question. Okay. The only thing I can say is maybe during that part of analysis, there's a point in which you asked them to tick like an extra row after you had done like you put like that part of you put the part on the row and column. They now said an extra row. So I don't know what that was for, but I think every other thing was fine with me.
No, okay. If you see the first person that was prof that was when the prof was trying. No, I just put that one. Actually, you don't need that one. I just say you should put it so that the normal chi-square. Let's see what it gives you, because the same data is 2 by 2 table. This data now is just like what we did before when we say sex and employment status, right? It's just only that this one is exposure to cigarette and lung cancer. So it's the same logic, 2 by 2. It will have its own chi-square. You have a corrected chi-square, whatever. But we are trying to shift that. That p-value, chi-square with p-value does not give much information. How do you quantify? That is why we now go to measure of association. Click the list. In your study, you are going to, if you do this study now, you are going to put the table, chi-square will be there. Yes, corrected, everything will be there, and put your odds ratio. I don't know if you understand me now. You still describe all those things. So that's what we are saying.
Okay.
You describe all those things. Okay.
Thank you. Thank you, sir.
You're welcome. So quickly before we go, this is 9 o'clock. Let me just stop recording now because so that it will not add volume to what we are.